In my presentation, I will talk about a stochastic Runge-Kutta method, which is meant to approximate solutions of deterministic systems of differential equations. The feature of this scheme are the following. It can be applied basically to large systems of ordinary differential equations if they originate from spatially discretized partial differential equations. In the first step, we use an approximation by a Markov jump process by the so-called stochastic direct simulation method, and by this we can simulate a full path of this jump process, and having this information, this full path, we can increase the precision by several steps of the type Picard iterations or Runge-Kutta type, or a combination of both. The method is based therefore on the predictor-corrector principle. The predictor is the simulated path of the Markov jump process, and after that we apply several correction steps, and the performance is comparable to standard deterministic solvers. So the overview of my talk will be the following. First, I will present some general features of dynamics of Markov jump processes and conditions under which they can approximate deterministic equations. Then a special case of Markov jump process, the so-called direct simulation method, developed for approximating solutions of ordinary differential equations. Next, I will show some improvements of the approximations by using Picard iterations or Runge-Kutta method. I will show some numerical examples of these methods, and in the end I will show another application at parameter identification for an ODE system, but instead of simulating a jump process we use now real data, and basically applying the same numerical scheme in order to optimize an error function which gives us the optimal parameter set, which matches the given data set. So let's start with the basics in a very general setting. At the beginning, we consider Markov jump processes with state space and general Polish space driven by a certain transition kernel R. And it is well known that the dynamics of such a Markov jump process can be written in the martingale form by using the infinitesimal generator. So psi is a continuous bounded function defined on the state space E, and we have the following dynamics, which we can see here. Lambda is the infinitesimal generator of the process, and m psi is a corresponding martingale. So the dynamics has basically two parts: a deterministic trend, which is given by the term containing the infinitesimal generator, given by this integral here, and the martingale part, it's a trendless stochastic noise, which are standard results, also known from Brownian motions or stochastic differential equations in a continuous case, but in our setting we discuss the case of Markov jump processes. So considering families of such Markov jump processes with values in this space of right continuous functions with left limits with values in E. In this space we can define the convergence by the so-called Skorohod topology, and under certain conditions we have the well-known relative compactness property, so the probability distributions of this family of a given subsequence converge weakly to a law of a limit process. Now, in certain situations, this limit process can be a deterministic function which solves a certain equation. A necessary condition can be that the second moments of the martingales tend to 0, but of course we need also other additional conditions. And practically, if you look back at the dynamics, if these martingale parts are very small in the limit, if they are vanishing, then we remain with the deterministic equation, which can be written in a so-called weak form in this way, but it can be also written in the usual form, as we can see in the next examples. Now let's get concrete. I will present next the so-called direct simulation method of ordinary differential equations. Let me start first with a single equation, and x dot equal f of x. So the equations are in this case time independent in the right hand side. So consider the following scheme. Delta t is a time interval which has to be specified. The value at the time x of t plus delta t is given by the value x of t plus or minus 1 over n. 1 over n is the fixed increment which we prescribed for the change of the approximation for the solution. Now, if the right hand side f is larger than 0, then the solution would increase. Then we have here plus 1 over n. If the right hand side f is negative, then the solution decreases, so you should have here minus 1 over n. But in order that this scheme is consistent, we need to take a very special form of this time interval delta t, namely exactly this n times the modulus of f of x of t, all of this expression to the power minus 1, so the inverse of this expression. Of course, if f is not equal to 0. Now, what are the features of this maybe unusual scheme? We change always the quantity x of t, which approximates the solution of our ordinary differential equation, every time by fixed increment 1 over n. This recalls of the weight of a numerical particle if you have n numerical particles. The time step is, however, not fixed but is adapted. We see here, first it depends on n. The larger n, so the smaller the change in the approximation of the solution of the equation, the smaller is also the time step delta t. And on the other hand, the larger the f, the right hand side, so the faster the rate of changing of the solution, then the time step delta t will become again smaller. So it's somehow adapted. But of course this approach does not work for systems in a deterministic framework, because every component has its own speed of change and the time steps required for changing every individual component are different. So for systems we can use the same principle but a random sampling, which I will present in the next slides. So consider now systems, autonomous systems of ODEs consisting of n equations. Under the standard assumption, the function f should be Lipschitz continuous. Now we change the components sequentially. We sample the component which has to be changed, and the probability distribution will be proportional. So the weight put on every component is proportional to the modulus of the right hand side. So if the right hand side is large, then the rate of changing that component will be large and that component will be sampled more frequently. So we consider therefore a Markov jump process with transitions given by the following scheme. From the current state we change it. In the new one we change only one component at one time. Component I is changed by plus or minus 1 over n depending on the sign of the fi of x, and the rate is given by this term, so it's proportional to n and to the modulus of the right hand side of the equation I. So we have a waiting time parameter, which is the parameter of the exponentially distributed waiting time given by this term, and the algorithm looks like this. We fix a maximal time for the simulation, and while our actual time t does not exceed this maximum, we do the following steps. So we have the approximation at time t, the state vector of our Markov jump process. We sample a component which will be changed with plus or minus 1 over n with probability proportional to the modulus of the right hand side of every equation. Now the time step is exponentially distributed with parameter lambda, and it is simulated as follows. U is a uniformly distributed random variable on 0, 1. We take minus the logarithm of u divided by lambda. This will be our delta t, our exponentially distributed waiting time. Now we select in this way the component which has to be changed and perform the jump. So the value will be plus or minus 1 over n depending on the sign of the right hand side, and set a new time as t plus delta t. Next we have to update some other values fj, because since we changed xi, the components j which are influenced by the component I which was just changed, then the probabilities for sampling next time will also change. So basically we update, because the equation j depends on the complete vector x of t. In the special case of discretized partial differential equation, we have only a few other components j which are influenced by the change of this component I. So this is the well-known direct simulation algorithm which was developed by Gillespie, also used by the present author in a paper of 2010. In general, because we have to update every time the values fj for all components j which are influenced by xi, it's efficient more or less if we have discretized partial differential equations, because then we have to change only a very few components, not large ODE systems which depend, well, the dependency matrix is a full matrix. Okay, now let me show how this method can be improved. The first possibility is to use Picard iterations. So consider again the system of ordinary differential equation, the autonomous system, but we write the system in an integral form on a small time interval. Now assume we have already computed an approximation at time t, and we want next to compute another approximation at time t plus h. H is the time discretization step. Now, on this time interval, we compute a predictor, basically by the previously described direct simulation method, and then we apply a Picard iteration in this way. So we just add to the known value x bar at the time t this integral, and this integral can be computed because x tilde is a simulated path of the Markov jump process, which is known with every jump because we simulated every jump of it. And the integrals are just integrals of step functions which can be updated after each jump of the process x tilde of s. So we can compute practically in parallel as we simulate the jump process. We can update also these Picard integrals, and we can compute the Picard approximation at time t plus h. Okay, the Runge-Kutta principle is another possibility. It looks similarly, but now here instead of integrating f of x tilde or of some other predictor, Q is now a polynomial which interpolates only some intermediate values on this interval. So we evaluate here the direct simulated process, which of course has to be simulated with every jump. or Picard iterations of it, but only at some equidistant points between t and t plus h. And then we compute the integral by a standard quadrature formula, which are well known from the numerical approximations of integrals. And I will show you some examples which lead to the well-known Runge-Kutta schemes. If you use the trapezoidal rule, you obtain a Runge-Kutta method of order 2. But of course, K1 and K2 are computed in the deterministic Runge-Kutta method by a different scheme. In our setting, these values are computed by simulating the predictor with means of the direct simulation method. We can also take in consideration a Runge-Kutta method of order 3, so a similar Runge-Kutta method similar to the deterministic method of order 3, which uses this integration formula, and also a Runge-Kutta method which is similar to the Runge-Kutta method of order 4, but not with the standard one. For the standard method, we have in the midpoint of the interval two different values which have no correspondent in our stochastic setting, but we can use a similar method with the so-called 3/8 rule. Okay, in the usual deterministic Runge-Kutta methods, these Ki are computed by the known Butcher tableau, but in our setting, these Ki are based on our directly simulated Markov jump process. So let me give you an example. A very simple equation. The exponential function has the property x prime x is equal to x, and the starting value is x of 0 is equal to 1. Now we will simulate a Markov jump process with jumps of magnitude 1/n, and since you have only one equation and not a system, okay, we can take, of course, random waiting times which have the mean value proportional to n times x tilde. So the stochastic algorithm, very simple for this example, is the following. Start at time t equal to 0 with initial value 1, and now fix a given time t star. We simulate first the waiting time, which is exponentially distributed with this parameter n times x is variable. U is again a uniformly distributed random variable on 0, 1. Then update the time, so t plus delta t. And now we update also the Picard integral. In this example, we just have to use this very simple formula. And we next update the jump process by adding 1/n. Okay, after reaching or exceeding the time t star, we compute the better approximations. We have two possibilities or a combination of both. First, the RK2 approximation. So we just take for the integral this formula, so 1/2 times t, which is instead of h as in the previous example, and we take here just k1 plus k2, which is f of the x, which is in our case exactly the x. This is, and in the next step we apply the Runge-Kutta approximation after previously applying the Picard approximation, which we compute in parallel with the jump process. So now let me show you the graphics. This is the path of our Markov jump process, which is simulated. Now we took the time 0.3. The exact value is given by this diamond symbol here. And now you see in this graph here an example where the path is quite far away from the exact value. But if you apply either Picard or Runge-Kutta 2 approximation, we get closer to the exact value, and if you apply both of them, we have a value which is even closer to this exact value. Now what are these curves here? These are magnified by the factor of 5 in order to be better visualized in the same picture. We have the errors of 48 simulations. The upper curve, the largest error, corresponds to the direct simulation method, which we can see has large fluctuations. Some paths have a very small error, but some other paths very large errors. And we are in this example, we have a path with I chose a path with a large error. Now if you apply either Runge-Kutta or Picard scheme, you have the next lines, the dotted and the dashed line, and the other dashed line, with more or less similar errors, but very low compared to the direct simulation method. And if you apply both of them, we see the continuous line here, which is even smaller. So these are the errors computed for 48 simulations from left to the right. So we see how this principle can improve the approximation property of a deterministic equation. Now, of course, there are also some other aspects which have to be discussed. How to sample, because in the usual application we have a large number of equations. If you think at specially discretized partial differential equations, we use a scheme or structure based on Hofmann trees, which uses a binary search, which is more efficient than the so-called inverse transform, which is basically linear search. Or the acceptance rejection method is not adequate in this context. The problem with this list of probabilities is that some of them are changing after every jump. So we have every time after every jump you have to update some values of this list, and this is done at best with the means of these Hofmann trees. But the convergence order is, as we have seen, increased by exploiting the full path simulation by this direct simulation method and applying after this further steps like Picard or Runge-Kutta steps. Now we can think also at adaptive Runge-Kutta methods, because the time step h was up to now fixed, but now we can consider also an adaptive method in the following way. So I will give the steps for the RK3 method. For the other methods we can use an analog procedure. So we fix a given number of jumps, and after this fixed number of jumps we have a time interval of length h1. This is the automatically adapted time step. This is the middle of the interval, because at the RK3 method we need also the midpoint value in an interval. Now the final value of this time interval is given by the double of h1. And we have three equidistant nodes where we can apply the usual quadrature formula. And we also can introduce the so-called multiple level Runge-Kutta methods, which I denote by RK2-3. Here are the basic steps, and on the next slide I will give the details. So the basic steps are the following. We use RK2 method, eventually plus Picard, on the first half of the interval and then on the second half of the interval, where we compute some approximation values. And then we compute our values K1, K2, K3 used in the RK3 scheme, not directly by the simulated process, by the direct simulation method, but already improved values where we previously have applied Picard or RK2 improvements. And next we compute a further improvement, but only at the time t plus h. H can be either fixed or it can be adapted as previously described. Here are the details, which can be read in the PDF file. It's written more explicitly what we do at every step. Basically, on the first half of the interval we perform RUNGE-KUTTA plus eventually PICARD, and on the second half of the interval the same, and using these improved values we have a further improvement by applying the RUNGE-3 formula. Now let's show some numerical experiments. We apply on the following test problem. This is a reaction diffusion equation modeling an ignition process. This is the nonlinear part here. We start with a condition constant value equal to 1. We consider this equation in the one dimension on the interval 0, 1, and with boundary conditions, Neumann condition on the left boundary point and constant boundary condition equal to 1 on the right point. And we consider a ODE system obtained by finite difference discretization with uniform grids. So the solution of this equation simulates a shock wave. So for a quite long time the solution does not change very fast, but starting with a given point, depending of course also on this parameter delta, we can see the formation of a wave which travels very fast to the right and until it reaches the right point of the interval. So we see here time steps, very small time steps, and the profile of the solution changes very fast. So we see here the results of the numerical simulation. We compare here several methods, with PICARD, without PICARD, adaptive methods, and basically we see that the method RUNGE-KUTTA using adapting time steps with or without PICARD, the difference is in this case not so much, but this performs best out of the considered methods. And you can take a look at the PDF file and try to see what every how every method performs. So we compare to a reference solution computed in MATLAB with high precision. The error is computed in the maximum norm, and we see here the logarithm in basis 10 of the error. So we see a very high precision here. It's about 10 to the minus 9 the error, so almost the same precision as the reference solution. But if we are happy with lower precision, then we can look at 10 to the minus 3, 10 to the minus 4, and it's up to us to choose the method which meets the requirements. Okay, the last part of my talk I will present another application, parameter identification in a system of equation which models the spread of an epidemic. In our case, we have some data which can be find on the internet for several countries. We have new cases, active cases, recoveries, deaths, and we can set up a model by ordinary differential equation, and the goal is to estimate the parameters of this equation in order to match the given data sets. And the principle is similar to the schemes I presented before, but instead of simulating a jump process, we use the increments of the data set. So our jump process, our random process, is in this case replaced by curves arising from real data. Now let's present first the basic model, SIR model, used in the epidemics. We have three different states: susceptible, infected, and recovered. And we have here the system consisting of three equations. Basically, we have the healthy people which were not infected yet. They can get infected by contact with the I group. That's why we have here the product I times S, You have to divide by n in order to have the correct scaling. This infected people then change into the group I, and the people recover with the rate alpha, and they then move into the group R of recovered people. This is the basic model. R of t, which we see here, is the so-called effective reproduction number, is the average number of further infections produced by the contacts with one infectious individual. Now we have to modify a little bit this system of equations, introducing two different states, I1 and I2. I1 means the state where the people is infected and can also infect others. I2 is a state where the people is still not reported as recovered but is not infectious anymore. And D is the category of death people, because the statistics also count the deaths due to this pandemic. Okay, here we have some parameters of the system. So R of t, as we saw already, is the production number. We have this time T-inf is the average time where a people is infectious to others. T-conf is convalescence time spent in the state I2, where a person is not reported yet as recovered. And we have also some death rates. So we have a system of ODEs with unknown parameters, but what we know is the data from the statistics. So we want to develop a method in order to estimate these parameters. The statistical data record the following values: the active cases, the new infections, the recoveries, and the deaths. So since we have the total population, assuming it is fixed, because the time interval is not so large, and this is a feasible approximation that the population size does not change significantly, we have this relation. So in fact it's sufficient to match only 3 out of 4 components. Okay, now we assume that R of t has constant values over 4 days. This is our assumption, so it does not change in our model every day, but only after 4 days. Now we have a general ODE system which depends on 2 types of parameters: a vector of time-dependent parameters and another vector of time-independent parameters. And of course we want to find a set of parameters such that the error in mean square sense between the solution of our system, depending on these unknown parameters, and the given data points is minimal. Okay, now we set up a function which returns the error, and of course we want to find a minimizer or a set of parameters which is very close to this minimizer. And for each set of parameters which you have, you need a solver for this ODE system. The solver has to be cheap and accurate because we perform many function calls. And for the solver we use the principle which we described before. I will not go into details because instead of using the direct simulation of a Markov jump process, we use just the increments of the data set. And here are given some further details how we handle the values at the midpoint of the intervals and so on. But we don't need to perform any simulation, but just using the increment of the dataset and then perform some Runge-Kutta steps which improve the approximation and which will deliver us a solution for the given parameter set, which is passed to the MATLAB function in order to compute the error and then trying to optimize the values of the parameter. Here again the assumptions, and the algorithm which we use is a splitting algorithm. We optimize first by keeping the time-dependent parameter fixed, and then optimize with respect to the time-independent vector of parameters, and then we switch the roles and keep P fixed and optimize with respect to R. And the computations are performed in MATLAB. So just I just show now the results for the case of Germany, where the model fits very well the data set. For other countries, one can notice that we have also some variations, because maybe the death rate is not constant or the rate of recoveries is not constant. This is basically the rate of reporting the recoveries, but for Germany the values fit very well also to the model. We see here the active cases, and the continuous red line is the computed solution of the system with the optimal parameter set. The green diamonds are the statistics for the recovered persons, and the green curve is the corresponding curve of the recovers of the system, of the components of the system computed with this optimal parameter set. Again, the similar is for the deaths. The black curve matches very well the black squares here. And here we have the curve I1, which is not in the statistics, but is the set of currently contagious people, so people which are infectious to others, and I2 is the component which denotes models the people which are not recovered yet, but they are not considered contagious to other people. So you can also notice that the solution is very sensitive regarding this effective reproduction number R of t. So the continuous line is the curve of active cases with the original one, but if we change it only by 5% larger or smaller, we obtain a change in the number of infected people by almost 100%. Here is almost the double value, and here it's the half of the value, only by 5% less. So it's very sensitive. And here you can see it in this table, compare the parameter values for several countries. You can look at the PDF file if you want to see how the differences between the countries can be explained. Okay, here are some references, and thank you for your attention.